Physical reality is currently described by two entirely incompatible rulebooks. On the macroscopic scale, general relativity models the universe as a smooth, unbroken space-time grid. But zoom in, and that geometric certainty completely shatters into an erratic, chaotic storm of probabilistic subatomic fluctuations. Quantum mechanics dictates that particles exist in a blur of multiple possible states, evolving linearly via the Schrödinger equation. The Schrödinger equation is a mathematical formula that describes how a quantum system evolves over time as a wave of probabilities. General relativity, conversely, demands that exact locations and masses strictly warp the fabric of space in a continuous, deterministic curve. Standard physics bypasses this contradiction by quarantining the math. Physicists apply the probabilistic quantum rules exclusively to microscopic particles, while general relativity is strictly reserved for massive objects like planets and stars. This artificial boundary leaves us without a coherent physical model. The inability to mathematically reconcile these two frameworks means our understanding of reality breaks down, exactly where the extreme mass of a massive dying star violently collapses into the infinitely microscopic point of a black hole singularity. Sir Roger Penrose completely rejects this compromise. He dismisses the orthodox Copenhagen interpretation, which asserts that a quantum system remains in a superposition of states until an observer measures it. He is equally dismissive of cosmic inflation, the standard model of the early universe that relies on highly improbable, short-lived scalar fields to explain the cosmos's uniformity. Penrose's skepticism carries immense weight. He was awarded the 2020 Nobel Prize for his rigorous proof that once a collapsing mass forms a trapped surface, the formation of a black hole singularity is an inevitable topological certainty, entirely independent of the collapsing object's symmetry. Penrose extends this geometric rigor to the entirety of physics. He argues that the physical topology of spacetime is not a passive backdrop. Instead, it is the active mechanism driving both the physical collapse of the quantum wave function and the cyclical infinite rebirth of the cosmos. To construct a unified model of the universe, we have to stop ignoring gravity at the quantum scale. We must trace the geometric architecture of space from microscopic Planck-length instabilities all the way to the conformal boundaries of the deep future. The standard model of quantum mechanics relies on observation to force a particle out of superposition and into a single definite state. Penrose argues this relies on an epistemic cheat. Relegating the collapse of the wave function to a mere updating of a conscious observer's knowledge fails to describe an objective physical reality. Together with physicist Lajos Diosy, he formulated the Diosy-Penrose model. The premise is rooted directly in general relativity. Gravity is not a force in space, but the curvature of space itself. Therefore, placing a particle with mass into a spatial superposition inherently demands a superposition of two entirely incompatible spacetime geometries. An isolated quantum wave packet starts as a stable probabilistic blur. As mass increases, spacetime must sustain contradictory mass distributions, unstable blisters. At the Planck scale, the gravitational self-energy difference hits this threshold equation. The blister ruptures, and the superposition objectively collapses into a single classical state. The math dictates a strict division. A microscopic object like an isolated electron generates virtually zero gravitational friction, allowing its collapse time to stretch for millions of years. But a macroscopic object, like a biological cell, possesses enough mass to force an immeasurably short collapse time of sub-attoseconds. Gravity is the physical mechanism enforcing classical reality. By forcing an unstable system to irrevocably choose a singular state, gravity-induced objective reduction actively generates the localized, forward-moving arrow of time. This irreversible, non-unitary collapse at the microscopic scale scales up to the macroscopic second law of thermodynamics. This law dictates that the total entropy, or measure of disorder, in a closed system must strictly increase over time. Tracing this thermodynamic arrow backward reveals a massive cosmological anomaly. Black holes possess the highest known entropy of any physical system. Therefore, if the universe began randomly, it should have overwhelmingly favored a chaotic, featureless sea of maximally entropic black holes. Our universe began as a smooth, isotropic thermal bath. Penrose calculated the phase space, the grid of all possible cosmic starting states. The probability of landing on this specific low-entropy universe by chance is 1 in 10 to the power of 10 to the 123. Rather than relying on the anthropic principle or invoking an infinite multiverse to explain this fine-tuning, Penrose proposed the Weyl curvature hypothesis as a purely geometric solution. The hypothesis establishes a strict kinematic constraint for the Big Bang. At the initial singularity, the Weyl tensor must be exactly 0. The Weyl tensor is the mathematical component of general relativity that describes the free, propagating gravitational degrees of freedom in empty space, manifesting as tidal forces and gravitational waves. At final singularities, like the interiors of supermassive black holes or a hypothetical Big Crunch, the math flips. As matter inevitably clumps together, the Weyl curvature diverges toward infinity, driving the massive increase in gravitational entropy. The extreme uniformity of the early universe is a strict geometric boundary condition. Setting the initial Weyl curvature to 0 physically outlaws any anti-thermodynamic behavior right at the exact moment of creation. Penrose incorporates this boundary condition into his most sweeping framework, conformal cyclic cosmology, or CCC. He proposes that the universe does not have a single absolute beginning or a final stagnant heat death. It iterates endlessly through infinite sequential cycles he calls eons. This requires rethinking physical scale. In physics, the measurement of space and the passage of time rely on the existence of mass. Massive particles act as the universe's internal clocks, ticking via the frequency of their quantum wave functions. If a universe contains only massless particles, like photons traveling at light speed, the concepts of time and distance lose their absolute physical definition. CCC imposes the mass fade-out condition. In the extreme remote future of an eon, all massive particles must eventually decay. The remaining supermassive black holes will ultimately evaporate entirely into massless Hawking radiation over unimaginable timescales. This diagram illustrates the conformal metric equation. In a universe of massless radiation, conformal symmetry is restored. Scale becomes undefined. Geometry preserves light cone angles, but discards size. The infinitely expanded future boundary squashes into a flat hypersurface, seamlessly attaching to the subsequent aeon's Big Bang. By shedding its mass and losing track of its own size, the dying breath of one universe becomes mathematically and physically indistinguishable from the explosive birth of the next. This introduces a severe theoretical paradox. The second law of thermodynamics dictates that a dying universe is in a state of maximal entropy. How can a maximally chaotic future spawn an exceptionally low-entropy Big Bang that perfectly satisfies the zero Weyl curvature requirement? Penrose resolves this by siding with Stephen Hawking's 1970s assertion: physical information crossing an event horizon is permanently destroyed when a black hole evaporates. In the CCC framework, the final evaporation of supermassive black holes destroys the vast majority of the universe's accumulated gravitational entropy. This massive loss of physical information effectively decouples the disorder from the active degrees of freedom, resetting the cosmic clock. In 2025, Penrose and physicist Christoph Meissner refined the transition math, introducing the gravitational wave epoch. Because the late universe is dominated by Hawking radiation, they postulate the universe transitions through a period dominated entirely by a gas of gravitational waves, governed purely by classical Weyl curvature. To balance the mass-energy conservation across the conformal crossover, Penrose proposes a dark matter candidate called the Erebon. These Planck-scale particles interact exclusively via gravitation and slowly decay entirely into gravitons over the history of an aeon, leaving no residual mass to disrupt the conformal boundary. Through the total evaporation of mass and the erasure of quantum information inside black holes, the universe transcends its own accumulated entropy. The slate is wiped clean, allowing the Weyl tensor to reset to 0 for a new eon. Penrose insists CCC makes testable empirical predictions. The cosmic microwave background, or CMB, is the faint radiation left over from the Big Bang. Because the conformal boundary preserves paths of light and gravitational waves, catastrophic events in a previous eon should leave discernible scars on our current CMB. The most prominent prediction is the existence of Hawking points. When supermassive black holes from the previous eon undergo their final explosive evaporation, the massive burst of energy is conformally compressed into a highly energetic, discrete point on the crossover surface. Penrose's team analyzed data from the Planck satellite and claimed to find these exact anomalous circular spots, measuring between 0.03 and 0.04 radians in angular radius. They assert these specific hotspots align perfectly across independent satellite datasets. His team also points to secondary evidence, concentric rings of anomalously low temperature variance in the CMB. These rings are theorized to be imprints of spherical gravitational waves generated by the collision and merger of supermassive black holes in the previous eon. If these statistical anomalies are real, they are the first observable fossils of a universe that existed before our Big Bang. The mainstream cosmological community remains intensely skeptical. Independent researchers cite the look elsewhere effect, demonstrating through rigorous simulation that these specific variance patterns are entirely expected statistical artifacts within standard cosmological models. The theoretical mechanics of CCC face equal scrutiny. The mass fade-out condition requires the spontaneous decay of perfectly stable particles, like electrons. This directly conflicts with the standard model of particle physics, specifically the Higgs mechanism, which imbues fundamental particles with a fixed rest mass, smooth early irregularities. CCC outsources this cosmic smoothing, relying instead on the infinite dark energy expansion of a past eon to level the horizon. Despite the friction, Penrose's framework forces theoretical physics to confront its deepest unresolved mysteries. He demands a physical mechanism for quantum wave collapse and rejects the highly improbable initial conditions required by inflationary scalar fields. Whether validated by future high-resolution data or remaining a brilliant theoretical outlier, Roger Penrose's cosmology asserts a profound continuity. From a microscopic wave function's collapse to the birth of the cosmos, every physical process must ultimately bow to the absolute geometry of spacetime.